Okay, we'd written down the expression for it last time. It was d2z, apart from all these factors of cs2 and g to the fourth, and the delta function for momentum conservation. That's always there. It was d2z mod z to the power, what was it? Alpha prime u by 2 minus 4. And 1 minus z to the power alpha prime t by 2 minus 4. And okay, so this is the expression that we're interested in studying in more detail. Okay, so we're going to study many aspects of this relationship. But before we actually study it in detail, just to remind you again that this expression is not viewed as an analytic function of u and t. It's not, well, first thing to remind you, alpha prime u plus t plus s was equal to minus 16. It's the kind of natural relationship we found last time. And, okay, so viewed as an analytic expression in u and t, it's not everywhere convergent. Okay, what's the condition for convergence? The condition for convergence is firstly that alpha prime u by 2 minus 4 is greater than minus 2, and alpha prime t by 2 minus 4 is greater than minus 2. But also that alpha prime u by 2 minus 4 plus alpha prime t by 2 minus 4 is that the sum of these two is less than minus 2. So it dies up at infinity. Let's quickly check. So what was it? So k1 plus k2 the whole thing squared plus k1 plus k3 the whole thing squared plus k1 plus k4 the whole thing squared, which is 3k1 squared, and then from that momentum conservation we got another minus 2k1, so that's k1 squared.
It's basically minus some over n squared.
Why minus? It's k1
squared is minus n1 squared, which is plus
k1 squared. K1 squared.
so all these are positive.
All these are positive, right? So then maybe I want to. Okay, good. But now let's remind ourselves what. So I'm getting confused even with the 16 now. What? So this is each of these is 4 by alpha prime. And there are 4 of them, right? Okay, good. So we've got plus 16. Maybe it was plus. Sorry. That's probably plus 16. Let me just check this. Just get everybody's using the same. He has minus 16, but then he puts a minus alpha prime u. So his u is probably minus of k1 plus k2 though. So, okay, so let's, maybe we should try to be consistent with quotients. Okay, so we put a minus here, a minus here. We change our definition to s is equal to minus of k1 plus k2 the whole thing squared, which is a good thing actually, because s will be positive at high energies this way. And that's it. T is equal to minus of k1 plus k3 the whole thing squared, and u is equal to minus of k1 squared. And then this thing is right with a minus. Okay, thank you, Doctor. Okay, so in order for for this to converge, the sum of these two from these two relations has to be greater than minus 4. It also has to be less than minus 2. Well, that's fine. So there's a window between minus 4 and minus 2 in which all three relations can be satisfied. Okay, so there's a place where it's convergent, so we evaluate it there and evaluate the entire expression by analytic continuation. Okay, so that's our goal. Okay, so in order to do this, we have to understand how to do this integral. So we're going to spend 10 minutes doing this integral. Okay, so we're going to spend 10 minutes doing the integral.
When are we looking at alpha when we go to minus 4, then
Yeah. Now with this should be minus and minus. This whole coefficient here has to be greater than minus 2 in order to get convergence at 0. The other coefficient has to be greater than minus 2 in order to get convergence at 1. And the sum of the two coefficients has to be less than minus 2 in order to get convergence at infinity. But it's important that these three conditions can simultaneously be fulfilled. Okay? So, the integral that we want to perform is an integral of the following form. It's an integral of the form mod z to the power 2a minus 2 1 minus z to the power 2b minus 2 d2z. Okay, where a is equal to minus of alpha prime u by 4 plus 1 b is equal to minus of alpha prime t by 4 plus 1. Okay, now let's see what we get from a plus b. You see, if we take a plus b, we find minus 2, and then from here we have alpha prime by 4. Okay, so let's write it down. Minus alpha prime u by 4 minus alpha prime t by 4. But remember that the sum of alpha prime by 4 with a minus sign is plus 4. So this thing can be written as a plus b is equal to minus 2 plus 4 plus alpha prime s. Okay, so if we define C is equal to alpha, so that's equal to 2 plus alpha prime s by 4. So if we define C is equal to 1 plus alpha prime s by 4, the symmetrical definition, then we see that we have a plus b plus c is equal to 1. Okay, so we have an a associated with u by I suppose I got a minus sign. Let's see, sorry. I got a minus sign. Yeah. Okay. So we have A associated with U by this formula, B associated with U with T by this formula, and C associated with S by the same formula. Okay. So As far as this integral is concerned, I'm going to just simply define a C such that a plus b plus c is equal to 1 and write the answer in some symmetrical way in terms of a, b and c, and we know what c is in terms of s. Okay, we can express everything in terms of 2 variables if we want, but it'll look more symmetrical if we express it in terms of 3. Okay? So now let's go ahead and do the integral. So this is the integral that we want to perform. So how are we going to do this integral?
So I think that to be c, right? 2 plus alpha prime s is 1.
No. I want a plus b plus c equal to 1. It's not equal to c. Okay. So let's do this integral. So we're interested in this integral here. And in order to do it, we're going to use a trick. Well, we're going to use the fact that mod z squared to the power a minus 1 is the same thing as dt t to the power minus a e to the power minus mod z squared t divided by 1 over gamma of, now what is it? If you have t to the power n plus 1, we have gamma of n. So minus a can be written as minus a minus 1 plus 1. So this is of minus a minus 1. Is that right? Let's see. Let me just make sure I've done that right. So we know that t to the n e to the power minus n dt is equal to n factorial, which is the same thing as gamma of n plus 1. So I should write 1 more than the coefficient that appears here. So I should have plus 1. Okay. I think this is fine. It's correct. So let's see. Why is this true? It's true by just doing the change of variables. Suppose we define a new variable t tilde, which is mod z squared times t. We'll absorb away the change to get the z mod z squared times a minus 1. That you can see by power counting. Okay? And then what remains is the definition of gamma of minus a plus 1. Okay, good. So similarly, we put in 1 minus z mod to the mod squared to the power b minus 1, other quantity we have here, is 1 over gamma of 1 minus b. 1 over gamma of 1 minus b times integral du u to the power minus b e to the power minus 1 minus 1 z mod squared times u. Okay, so let's insert these identities into the integral expression that we want to compute. So what do we get? We get d2z. Okay, then we get du dt divided by gamma of 1 minus a, gamma of 1 minus b times exponential of, and now let's write z as equal to x plus iy. Okay, so we get minus t into x squared plus y squared and minus u into 1 minus x the whole thing squared plus y squared. Okay, now we're using Polchinski's convention for all numbers here. So for Polchinski, d2z is equal to dz times dz bar. which is twice of dx dy. Because the determinant between z and z bar, x and y, the Jacobian determinant is 2. Okay? So, this quantity now can be written as 2 times dt, du, dx, dy times axis times this exponential. And let's simplify the exponential. So we simplify the exponential by completing squares. So it's minus t plus u into x into okay, let's first write it out. So x squared plus y squared. Then there is the linear term in x, which is plus 2xu, and then there's the constant piece, which is minus u. And we of course have, here we had of course also the t to the power minus a and u to the power minus b. So we carry that one as well. T to the power minus a, u to the power minus b. Okay, so the next step what we do is to complete the square and the exponent. So we have 2t to the power minus a, u to the power minus b, dt, du, dx, dy, exponential of okay, so now when we complete the square, we get something. So some shifted x. Okay, so it's t plus u into x minus what's the shift? It's u by t plus u plus y squared. And then we have to do the subtraction here, which gives us minus u and then plus of u squared over t plus. Okay, so that's 2t to the power minus a, u to the power minus b, dt, du, dx, dy, exponential of minus t plus u into this square business. And then let's simplify this. That is equal to minus of tu divided by t. Okay, so now the next stage, of course, we do the Gaussian integrals in x, in the shifted x and y. So that gets rid of the x and y integrals. And we pick up a factor of square root pi, the whole thing squared. So that's 2 pi. I mean, you have 2 here, so that's 2 pi times integral t to the power minus a, u to the power minus b, du t exponential of minus tu by t plus. Okay. I'm going through this in some body detail, by the way, because this is, one of the one of the first formula string theory, 6 years ago. Okay. So now the next step. And the next step, what we do, we've done some simplification, but we've still got 2 integrals to do. How do we do? Okay. So the next step, what we do is to say, well, let's switch variables to an overall scale in TU space and a ratio. So let t is equal to be alpha x and u be equal to 1 minus x into alpha. Okay, so let's work out the determinant, the Jacobian for this change of variables. So dt by dx is alpha. Okay, let's say dt by d alpha is x, dt by dx is alpha, du by d alpha is 1 minus x, and du by dx is minus alpha. So this is the determinant of change of variables, which is equal to, whose modulus is equal to 1. Right? The x alpha pieces cancel. Okay, so there's no Jacobian limitation. Fine. So we can rewrite this expression here as 2 pi. Then this becomes then the integral over alpha is distributed. Right? So what's the integral over alpha? So we get 2 pi alpha to the power minus so this Jacobian is equal to alpha. Alpha. So alpha to the power minus u minus a minus b. We have a plus 1. Okay? Times, then we have x to the power a, 1 minus x to the power b. And then we have exponential of minus alpha into x into 1 minus x. It doesn't, Jacobians are, what? I mean, it's a positive integral. We'll worry about the sign. Yeah, I mean, we don't know. Okay. So, now that we do the integral over alpha, so the integral over alpha gives us what? Firstly, we get gamma of a plus of minus a plus b. Right? And somewhere along the way we lost our 1 over gammas. We've lost that 1 over gammas, we put them back in. It's just both spaces a little bit. So we have 2 pi, okay, let's put it back in now. So gamma of minus a minus b over gamma of 1 minus a into gamma of 1 minus b. Okay? Times we get this factor of x into 1 minus x from power. Okay? Times the factor of x into 1 minus x from power. Counting. For each factor of alpha, we should get a 1 over x into 1 minus x. Okay? So, we get integral dx x to the power minus b plus 2 1 minus x to the power minus a plus 2. So each factor of alpha has a 1 over. So, sorry. Okay, so we should, when we have an alpha, we should take it to x to the power minus 1, 1 minus x to the power minus 1. So we have this factor, but we have an alpha plus 2. So this should be replaced by x to the power minus 1, 1 minus x to the power minus 1 into minus, so we should make those pluses. So a plus b minus 2. 2 because there was a d alpha in there. Okay? And we have x to the power a, 1 minus x to the power b. All I have to say. Let's see.
The Gaussian integral. pi over alpha.
Thank you. That's important. Thank you. We should have got a factor of 1 over t plus u.
1 over root t plus u into root
Just 1 over root t plus u squared. Because it's x squared and y squared. So just a factor of 1 over t plus u. Yeah. So that would be another factor of alpha. Oh my. I hope we can trace this to the length. I may have to repeat it, which is saying something like that. Is this clear? Thank you for pointing it out. So we have a 1 over t plus u. Thank you.
There's a redefinition of x involved. I think the coefficient of x square is different from the coefficient of
No, it's not different from the coefficient. X squared and x minus shift.
Yes,
but there is a division by t plus u.
Right? It doesn't matter. If you write it as
Oh, okay. It's x minus u by t plus u.
yeah. Okay. So there's 1 over t plus u here. Maybe I'll at some point quote you the answer. But let's try. Okay, maybe it's not. But okay, let's try it another time. So, okay. So what do we get? We had a t to the power minus a. Yeah, we had t to the power minus a, u to the power minus b, du dt. So the powers of alpha we now get by homogeneity, right? So it's alpha to the power minus a minus b plus 1. Sorry, no, there's no plus 1 here, but there'll be the d alpha. Right. This just cancels the alpha we get from the Jacobian. Right, so it's same. Okay. So this gives us a gamma of plus 1. T to the n is gamma of n plus 1. Plus 1. Okay. Let me just. Let's take it here. Okay. So, okay. So what do we have? We have so the remaining integral is dx into x to the. Did I get this part right? Sorry. A plus b minus 1. Minus 1 here. Right. We have x to the power 2a plus b minus 1. 1 minus x to the power 2b plus a minus 1. Okay, I'm hoping this is the right thing. But let's see. Now, the next step is to use the formula. The next step is to use the formula for the beta function. You know, if you had this thing would be hey, it's not very good. Maybe it's okay. Let's just go through. this thing by, there's this beta function formula which tells you that this thing is equal to gamma of 2a plus b into gamma of 2b plus a into gamma of the sum of the two.
What are the range of integration?
Always, man. Okay. So the range of integration for t and u is 0 to infinity.
So alpha
And alpha and x goes from 0 to 1, and alpha goes from 0 to infinity. Right? I was messed up somewhere when. I've messed up on some sign somewhere. Hey, just give me 1 minute. I'm sorry about this. There are previously different variables and then so I have to do with Chinsky lines. You would like is give me 1 more minute. I messed up. Oh. This integral is 0. This is the. I somehow feel I should have done these extra powers with a negative sign. I don't think it makes sense. Or the others. These were the negative sign, right? This had minus a, this had minus a. Because it was t to the power minus a, and t was x times alpha. Okay, sorry. So next modification. So this is minus and minus. This part is correct, but this is wrong. So what do we get here? Here we get b minus 1. And here we get a minus 1. This is good much better. Okay, so now this thing, gamma of b times gamma of a. You remember this classic formula. You remember that you have once learned this classic formula. It's Euler beta function formula. Yeah, this integral can be valued in terms of gamma functions. In terms of gamma of b plus a. Okay. So we finished. We have to multiply this with this, and that's our answer. Okay. So what's the answer? It's 2 pi. Now we use the fact that 1 minus a minus b is c. So a plus b plus c is equal to 1. Okay, so it's 2 pi into gamma of a, gamma of b, gamma of c divided by, and then we use the fact that b plus a is 1 minus c, gamma of 1 minus a, gamma of 1 minus b, the gamma of 1 minus c. Is this clear? Clear, everyone? Okay, very good. So now we just have to remember what A, B, and C were. So we've written that down on the board. What was it? A was equal to minus of alpha prime u by 4 plus 1, and similarly for B and C. Okay? S is equal to, well, so when we have all these delta functions which I never write down, times CS2 times G tachyon to the power 4 times 2 pi times gamma of, now we had an ABC in the denominator, in the numerator, so minus 1 minus alpha prime u by 2 by 4. Okay, let me write it in the next line. Into gamma of minus 1 minus alpha prime u by 4, gamma of minus 1 minus alpha prime s by 4, gamma of minus 1 minus alpha prime t by 4. The whole divided by. Now we need 1 minus a. So that is divided by gamma of 2 plus alpha prime u by 4, gamma of 2 plus alpha prime t by 4, gamma of 2 plus alpha prime s. Okay, into, this is 2 pi to the power 26 times the delta function of sum over omega. Let me go. If that you can see. Okay, so that's our final formula. This is the S matrix for the scattering of four tangents. You see that this claim that we made in the last class, that even though it wasn't obviously symmetric under the interchange of S, T and U, the answer is manifest in this form, the formula. Okay, any questions or comments about this before we proceed to study this? Okay.
This part is alpha prime t by 4 or
what is always equal to?
the alpha prime t is u by 4.
Alpha prime.
This part of the thing. Alpha prime u by 4.
Alpha prime. No, you see, at the moment it's a function of an arbitrary complex number. It's like there's no claim about positivity. Wait up. Okay. So let's just start with immediately address the question that Jyotirmoy had. Okay. So the question that Jyotirmoy had was, well, this formula has poles. Okay. So what do the poles be? So let's first understand what the first pole is. So let's suppose we're working with the variable s. So that it's completely symmetrical for three variables. So any statement about poles in one variable will be reflected in the other. So let's say we're working with the variable s. Okay? So now s, the way we've done it, is something positive and gets increasingly positive as we go to higher and higher energies. Okay? Therefore, this gamma function here gets increasingly negative as we go to higher and higher energies. So we keep running into more and more poles. This gamma of a negative integer has a pole. So let's say what the first one is, what the lowest energy pole is. Okay? So the first time we hit a pole is when this object goes to 0. So we have minus 1 minus alpha prime s by 4 is equal to 0. Okay, that's the first time we hit the pole in the variable s. That's the smallest value of s for which we hit the pole. And that occurs and s is equal to minus 4 by alpha. Now what does it mean to have a pole at s equals minus 4 by alpha? Somebody tell me the Exactly. You see what's happening is that we've already seen that our theory has a 3 tachyon vertex. In fact, we calculated. So, if you have 2 tachyons propagating, getting scattered into a third one, we can then contributes to what angles? So this diagram that I drawn, all lines here are tangents. This contribution, you see, this answers the full answer for the S matrix. It's not, some effective action from which you have to build trees. It's the full answer for the S matrix. So it includes tree level exchange of all particles in the middle. Okay? So every particle that you can get by colliding two cations and running in a channel will contribute, and each of these contributions will give you a pole. Okay? So in particular, one is the mass spectrum of string theory. But the mass spectrum of string, the spectrum of closed strings is at m squared equals 4 by alpha prime into n minus 1, where n is all positive integers, the number operator of the oscillators. Okay? So, from general considerations, we should expect a pole in S at every value of S that takes this form for any integer n. Now let's check, when do we actually have poles? When do we actually have poles? We have poles when alpha prime S by 4 minus 1 is equal to minus n, which tells you that's when alpha prime S by 4 is equal to n minus 1. So you put the 4 by, so S is equal to 4 by alpha prime n minus 1. We see it's exactly the same places. Okay, so our scattering amplitude has poles, but it has poles exactly where we should expect them to be for physical purposes. Okay, now that we understand this, of course it's the same in the T channel or the U channel, it's the same thing. Now that we understand this, okay, the next thing we should do is to try to understand this a little better. So, you say, well, okay, if you're so smart, you should be able to, not just say it has a pole, but check that the residue is the right thing. Okay? So let's see. So what did we have? We had that this scattering amplitude, remember, was GTQ times CS. The other one was the same thing. So the pole from this process, the residue of the pole should be GT to the 6 times CS2 squared should be equal to the residue. Okay? But now what do we find for the residue? We find for the residue GT to the 4th times CS2 times what? Well, we should plug alpha prime. We should plug S is equal to minus of 4 by alpha prime into this. Okay, suppose we plug S is equal to minus of 4 by alpha prime into this. What do we get? Well, let's see. Firstly, from here, we get gamma of 1, which is 1. But then we have all this other stuff floating around. But I claim that the other stuff cancels. Let's see how that works. It's actually easiest to see. You have the formula gamma A, gamma B, gamma C over gamma of 1 minus A, gamma of 1 minus B, gamma of 1 minus C. And when we got our first pole is when, let's say, A was equal to 0. Okay? So where A is equal to 0, B is 1 minus C. And C is 1 minus B. So this gamma of B cancels the gamma of 1 minus C. And gamma of C cancels gamma of 1 minus B. Okay? So you see that the residue to this pole, the residue here, so I'm claiming that the structure, it's the same thing here, it's harder to see because there are more quiche. Yeah? So we set S to the same, we set S equal to 0, and we get, what do we get? We get that in the neighborhood of that, sorry, we said S equals, this thing equals 0. We get that in the neighborhood of that, we get gt to the 4 times cs2 times 2 pi times 1 over this quantity. So 1 over s minus alpha prime by 4 into s minus 4, s plus 4. Right? I've just written this quantity, its modulus value in the appropriate way. I didn't define it. What's this? S. Is it clear? Okay? So in the neighborhood of this pole, this is what that function looks like. So what's the residue of the pole? Well, the residue of the pole in S plus 4 by alpha prime is alpha, so that's 8 pi by alpha prime times cs2 times 2 pi, which times gt to the 4, which should be the same thing as gt to the 6 times cs2. Now you see, the point is the following. We didn't know with what number we should put each vertex operator to start. That's why we had this GT, which was some free number. Now this relationship in physics tells us that these two should be equal. So we cancel this to make this square, we cancel one factor of CS2, and we find that GT squared is equal to 8 pi by alpha prime divided by CS2. So you want to treat all these things seriously from unitarity, from basic rules of unitarity. Okay, we obtain what the right value is for the for the prefactor that we have to put behind the tachyons calculation. Okay, so there's no check here, but it's a way of determining what the right answer is for the prefactor. Now, of course, once we determine that, now if we calculate 5 and 6 point functions, the tachyon, then there will be checks. Okay, and those all work out. We're not going to do it. We're not going to try to do that. But if we determine it once and for all, and now every time you have a tachyon operator, this is what you have to put in. Is this clear? Okay. Now that we have what GT squared is in terms of CS2, let's go back and look at our 3-point function calculation involving one graviton and 2 tachyons, and see what we can say about the normalization. If you remember from last time, we had an alpha prime by 4 the whole thing square times k23 mu e mu. We had the amplitude for one graviton to scatter to a graviton in particle 1 to scatter to tachyons which are particles 2 and 3 to be proportional to this object. The alpha prime by 4 there was a factor of 2 in our basic formula for del x, and there was a second factor of 2 because we took k2 and made it k2 minus k3 by 2. Okay. Now this was dressed with a GT square and then a G masses. Okay? It was also the rest with the CS. But now GT squared times CS2 we know. It's 8 pi by alpha. So this thing is the same thing as GM times alpha prime by 2. And then there's a pi. Okay, as I'm not giving that signs and big factors of the I. Yeah. So alpha prime by 2 times pi times k to the 3 mu, k to the 3 mu times e mu times g. Oops, gm. Last class, you might remember, I was getting confused about this normalization not matching with Polchinski. But Polchinski then is plugged in this relationship. So that's why I got to 1 alpha prime. And this matches with my case. Okay, very good. So this is now the 3-point function of 2 tachyons and the graviton, but it's still not clear what it is because we still don't know what GM is, what G for the master state, for the graviton is. So how do we compute that? Well, I'm not going to actually go through the calculation because it's not difficult to do, but I'm not going to go through it to get all the numbers straight. But let me just indicate how it works. Okay? Once again, we want to take this 4-point function calculation and factorize it on the pole. But this time we won't be the pole at s is equal to 4 by alpha prime. It will be the pole at s is equal to 0. Okay? So when we factorize it in the pole, we get 2 factors of this vertex. Okay? Divided by the pole. So the residue should be 2 factors of this vertex divided by the pole. Now, there's not one massless particle, there are many massless particles. We're supposed to sum over all massless particles in the game. So we get factors of this, another factor with another E prime here, factors of momentum, and then you're supposed to sum over all polarizations. Now, sum over polarizations can be done giving you a completeness thing. Okay? And so when you do that, and you plug it all in, you get some powers of T. Right? Because you have 2 factors of momentum at each vertex. So you get 4 factors of momentum at the end, which will in the end turn into something invariant. So it will be some power of T that is quadratic. Okay? So you get some power of T or T. Just schematically it's k to the 4. That you get on your pole. Okay, now you can go back and ask, is that the kind of residue that you actually get from the 4-point function? Okay, so let's study just without putting it for ABCR for a moment. So suppose we study for ABCR. Suppose we look at gamma of A, gamma B, gamma C over gamma of 1 minus A, gamma of 1 minus B, gamma of 1 minus C. We saw that if we looked at the pole at A equals 0, the answer was independent of B and C. The residue to that pole was independent. So now we can ask, is this going to continue? If we look at the residue of the pole at A equals minus 1, is the answer still independent of B and C? And the answer is no, it isn't. So if we look at the pole at A equals, let's say, minus N, okay, then B will be equal to, so now let's say that we can substitute, since A plus B plus C is equal to 1, okay, since A plus B plus C is equal to 1, we can substitute for one of these. So let's say we substitute for C in terms of B. So C will be equal to 1 plus plus B minus B. Okay, so if A is equal to minus N, C will be equal to this. So what we will get is something of the form 1 by A times N factorial times gamma of B, gamma of 1 plus N minus B over gamma of 1 minus B times gamma of 1 minus, so 1 plus b minus n. Now when n was equal to 0, the 1 is cancelled, sorry, b minus n. Right? So when n was equal to 0, this cancelled this, and we were very happy. Okay? But when n is not equal to 0, we don't have perfect cancellation. However, we can use properties of the gamma functions. The fact that gamma of n plus 1 is n times gamma of n. We get a simple formula for this. Let's do it for n equals 1. So for n equals 1, what do we have? We have gamma of b, gamma of 2 minus b over gamma of 1 minus b into gamma of b minus 1. Now this thing is equal to b minus 1 into gamma of b minus 1. And this thing is equal to 1 minus b into gamma of 1 minus b. So we get b minus 1 into 1 minus b, okay, into 1. Using the formula, the gamma of n plus 1 is n times gamma of n. Okay, you can check more generally that if we went, well, you can easily work out the formula that you get at high end. It's like b minus 1 the whole thing squared to b minus 2 the whole thing squared. Okay, but let's remember in our context what this. Okay, I won't even go through it much more. You can work this out in terms of ST and U, compare with, convert that to momenta, see that it matches what you get from this thing. The key point is that something quadratic in the T's, okay, which is something quadratic in the momenta, as you expected from this, and then you can try to work it out in more detail, work out the numbers. Okay, I'm not going to try to work it out in much more detail. Very good. Sorry. So the key point here that I forgot to say, that when you do this, of course, you get all the momentum part matching, but there's some number that's left. Okay, and then the GM will just be fixed by its matching. And when you do that carefully, what you find GM is 2 divided by R. You get GM is equal to G tachyon times. You see, you have 2 factors of GM left, and you have 2. You get GM is equal to G tach. You see, you have the 3 point scattering was GT. Had a GT square times GM, and the 4-point function has a GT to the 4. So the GT's cancel, and then you get GM but there's a CS2 that's left over, which you can re-express in terms of GT. So in the end, when you do it, you get GM is equal to GT 2 divided by 4. Okay. Now there's actually another way. Of working out the relative ratio between these two numbers, and that is through the state operator. You see, the logic for these vertex operators was they were the operator that corresponded to a given state. Now you can ask, but with what normalization should we put the operator? Well, if you think of it through the state operator map, there's no ambiguity. We should put the state with the normalization 1 and work out the operator that is dual to that state with normalization 1. Now, in addition to all of that, you may want to put an overall factor because you're computing an S matrix. But the relative normalization between the 2 operators of 2 different things should be fixed by this. Okay? So I'm going to leave this for you as an exercise. Work out the relative normalization from the state operator map of the vertex operators for the massless states compared to the vertex operators for the tachyon. Okay? Being careful to ensure that the states to which your operators are dual are unit normalized. Okay? You'll find the same ratio. Okay? So there's some sort of check. For this program. So once you get confident about this logic, you can just use the state operator map to find the coefficient that you put for behind various vertex operators, rather than calculating it every time, and perhaps perform a few checks based on it. Is this clear? Okay, great. Now the last thing I wanted to, the last two things I wanted to tell you about before we quickly terminate so we can prepare for load and stock, is about the high energy behavior. It's about the high energy behavior of these activities. Actually, before that, let me quickly say one thing. You know, we had all this fancy analysis involving the exact answer in order to determine the poles and the residues. But if we just want to determine the first pole, it's actually very easy to do directly from the first integral representation. Okay? And that's, we have z to the power minus alpha prime by 4u minus 4 times stuff as regular, at z equals 0. And we want to do this integral. We want to do the integral d2z. Okay? So what do? We want the neighborhood of that thing being about to become divergent. So we take this and we convert it into a radial and an angle integral. We get 4 pi from the angle integral because our measure d2z is twice the x dy. Okay? Then this becomes r dr r to the power minus alpha prime u by 4 minus 4 minus 1. What was it? Sorry, let me say the formula like by 2 minus alpha prime u by 2 minus. Okay, and then then as long as this is sufficiently negative so that it's convergent, we know the answer to this integral. It is r to the power n has derivative n. So if we integrate r to the power n, we get 1 over n plus 1. Fine. So we get 1 over alpha prime u by 2 plus 2. Yeah, yes. Right. This has become minus 3 and then this plus 1. Okay? So that's 8 pi over alpha prime u plus 8 pi by alpha prime into u plus alpha prime by 4. It's the same polynomial. Okay? So, if you just want the residue of the pole, at least for the first guy, this is the simplest way to get it, just to check that we haven't done anything crazy now. Exactly, evaluation of the integral. Okay, last thing next. Just so that next time we go on to something else. The last thing I want to tell you about is the high energy behavior of these activities. Okay, so for that purpose I need to rewrite the scattering amplitude in terms of ST and U. I'm going to ask for help from somebody who's taking down notes. So what was it? It was 2 pi times product of 3 gammas divided by product of 3 gammas. Can you help me fill up the arguments of these?
Minus 1 minus alpha prime.
Minus 1 minus alpha prime x by 4.
Okay.
Okay, and then similarly.
Right.
And
plus alpha prime u by 4.
And similarly. Okay. So now there are 2 high energy limits that are of interest for different purposes. The first high energy limit that's of interest is the limit in which we take S goes to infinity, T goes to infinity, U goes to infinity. Back to, with by modulus of S goes to infinity, modulus of T goes to infinity, modulus of T goes to infinity. Because S plus T plus U is equal to 1, so they can't all go to positive infinity, but they can all become very large and continue to obey F plus T plus U equals 1. So, before working on the answer there, let me remind you what that means physically. So, suppose you've got some particles, suppose we work in the center of mass frame, and we have two particles colliding at each other in the x direction. So, we have particles whose energies come. This is K1, let's say, and K2 is momentum is added to 0, so we're at the center of mass frame, but at the time the energy is not added to 0. So we've got, and we probably want, right? Okay, so suppose we've got things coming together like this. Okay, and say K3 is what K1 becomes after its deviation. So it becomes square root S by 2 times 1 cos theta sin theta 1. So theta was 0, we know scattering. And K4 was square root S by 2, 1 minus cos theta minus sin theta 0. So the momentum continues to add to 0 after scattering. 0. Thank you. Okay, so this is the momentum diagram, something that comes in like this and then scatters at an angle theta. K1, K3, K2, and K4. Okay, so now it's a simple matter with this momentum configuration to calculate S, T, and U. For instance, S is S. We've set it up that way. You add the two of these, the momentum cancels, the factor of 2 goes here, then you take the square and get S. Okay? But now we want to calculate T. Basically, the point is that suppose you keep the angle fixed, suppose you keep theta to be some fixed angle, and take S to infinity, then everything will go to infinity. S will go to infinity, T will go to infinity, U will go to infinity, because everything is multiplying some fixed function of theta with this factor x. So, this limit here corresponds to high energy fixed angle state. Keep angles fixed, take the energy very large, study what's going on. Here the limit S, T, U are going very much. Okay, so the question we want to ask is what happens to our formula in this high energy fixed angle scattering? Well, so when everything is very large, we can just use the crudest approximation that there is for a gamma function. That is, gamma of x is equal to x to the power x plus times corrections. Those corrections will all be something first. Okay, so gamma of x is x to the power x. So here what do we have? We can forget about the 1s and 2s and so on. So, what do we have in S? We have up here, it's minus alpha prime S by 4 to the power minus alpha prime S by 4. And in the denominator, we have alpha prime S by 4 to the power alpha prime S by 4. The modulus of this, if we take modulus, this goes like alpha prime S by 4 to the power minus alpha prime S by 2. Okay? Or it's often written as e to the power minus e to the power minus alpha prime S by 2 times log of S. Okay. The key point when S is large, this log S is a slowly growing function. So roughly speaking, well, this is even further down, but roughly speaking, this amplitude is exponentially damped at large S. And the thing that sets the dimensions for this exponential damping is the string scale. Okay, now can you give me a physical interpretation? Okay, so the first thing is this is a very important point. It's a very important point that string scattering becomes very small at very high energies. It's very important because it's the opposite of the behavior of graviton-graviton scattering from the Einstein approach. Graviton-graviton scattering becomes very large apparently at high energies. The effective gravitational coupling involves powers of the momentum. Okay? So this exponential damping of high energy amplitudes, which is a general feature of string theory, okay, is at the heart of the finiteness of string theory. We haven't yet shown that you know that string loop amplitudes are finite. They don't need to be cut off. The physical reason for this is the exponential damping. Things don't interact very much at very high energies. Okay. Now, can you give me a physical interpretation of exponential damping? Have you in your study of physics before encountered an exponential behavior of a scattering amplitude? Yeah, in a very important experiment, something changed physics at the turn of the last century. You know, Rutherford scattering. You know, the way Rutherford discovered the structure of the atom was by taking electrons and throwing at the atom. And he'd done the calculation that showed him that they knew that there were positive and negative charges of the atom. One model was this, plum pudding model of the atom. There's this large soup of, some model in which the negative charge of the atom, and maybe the positive, I don't even know what, but so the charge of the atom is uniformly spread over the radius of the atom. Had that been the case, the scattering of electrons from the atom would have been very, very small. Okay? It's just a general feature of Fourier transformation. That if you scatter at a small wavelength over a source that is very large, the part of the source that you scatter from is the part that clicks with your Fourier transform. And if it's like, if it has a length scale that is very much larger than the length scale associated with your scattering length, you get exponential suppression just from the Fourier transform. The Fourier transform of a Gaussian is a Gaussian. It is exponentially suppressed at very, very high gain. Okay? That's not what Rutherford found. Rutherford found is every once in a while you get these zings corresponding to the fact that the source that was doing the scattering was very small. It was this localized nucleus. This is a totally important experiment. Turn of the last century. Now what we're seeing in string theory is the opposite of that behavior. What we're seeing is that when we scatter energies high compared to the string scale, when we make our wavelength small compared to string scale, we get this exponential damping. So it's what Rutherford had originally expected. It tells you that string states are big fuzzy objects on string size, on string scale, and the form factor, which is a fancy way of saying Fourier transform, of the source through which scattering occurs, causes exponential damping as strings scattering against each other at very high energies. The key to the exponential damping is that strings are big fuzzy objects of string scale. Do we have to stop, Ajay? Yeah, we have to stop. Okay, it's just one more minute. Okay, so that's what happens at high energy fixed scattering. Now there is another thing that we have to that was historically and is physically important in string theory, and that is high energy scattering, not at fixed angles, but when you take S large, but at fixed T. Now you can ask, what the hell is that? And you can check by going through the formulae that corresponds to taking S to infinity while keeping S times theta squared fixed. So you're looking at low angle scattering, and how low the angle is goes to the angle goes to 0 as S goes to infinity. Okay? Okay, I'm going to leave it to you as an exercise, which I really urge you guys to do. It's 5 minutes, but please do it. When you calculate, you use the Stirling approximation on this stuff in the large S fixed T limit. Remember, if you take large S and fixed T, you must be taking large U as well, because S plus T plus U is equal to 1. Okay, so large S fixed T limit. What you'll find is S to the power. Which is the right all these formulas in such a crazy way. -2.